All right, guys. So today we're talking about modeling exponential growth. So this formula here is our general exponential growth model. And I just wanted to break it down real quick. You can see here that f of t is going to represent whatever value or population that we're modeling, right? So if I'm modeling the growth of a city's population, that would be f of t. It's the population at any given time t, right? A here represents the starting value. So let's keep my city example going. If I measure a city's population at some given time, right, and then I decided to make that the starting, like the start of my data collection, that would be the starting value. So the starting value is just basically whatever population or measurement that you've taken at the very beginning, right? E is Euler's number. It's that it's that rational number that just goes on forever. It's very similar to pi in its properties, and it's very, very important for us in exponential growth. R here in the exponent is the growth rate. This thing is the key for us in most of our exponential growth modeling problems. It's very common that we have to solve for the growth rate because that's not something that you can usually just be given. Usually what's going on is that you have data and you have to extrapolate from that data. You have to calculate the growth rate, right? And finally, we have t here, and that's just going to represent time. So the idea is that as time goes on, our population or value goes up when it's in exponential growth, right? So let's go ahead and check out an example of this. And the example I would love to use is my favorite example of exponential growth, rabbits in Australia. So rabbits are an invasive species in Australia. What that means that there didn't exist rabbits in Australia originally, right? There were no rabbits there until some colonists brought over rabbits and released them back in like 1859, right? Something that's crazy that happened though, the rabbits, because they are not a native species in Australia, what that means is they have no natural predators. So nothing really naturally hunts the rabbits, which allows them to have their population grow exponentially, right? Nothing's inhibiting their growth. Um, so 10 years later, the population of rabbits in Australia had grown so large that actually they recorded 2 million rabbits being trapped and sold per year without showing any significant decline in the population. People didn't even notice any less rabbits, even though they had caught 2 million of them. So we're going to use this to try to calculate a exponential growth model for the rabbit population in Australia. To start off, let's suppose that there were 100 rabbits to start with in 1859. All right. That's about. It started with actually like one dude released 24 rabbits, but other people also released rabbits after they heard what that guy did because they all wanted to hunt the rabbits for game, right? They thought it'd be fun to have rabbits in the wild like back in England so that they can hunt them. So we start with 100 rabbits in 1859. And then let's say that there's 10 million rabbits in 1869. That way a decrease in population of 2 million doesn't really get noticed as much, right? Um, we want to create an exponential growth model for the rabbit population in Australia. So to get started, let's look back at our exponential growth model. I'm going to use P of t this time because P represents population over time. So the population of rabbits over time would be equal to our starting value times E to the power of the growth rate times time, right? So let's use the data we were given and plug it into this function. So the first thing we know is that we started with 100 rabbits, right? That's going to be our starting value. So we have 100 rabbits. The growth rate we do not know. That's something we're going to have to calculate. And then we have t and we have p of t, right? Well, this is where our second value will come in. If we've been given a starting value, that lets us fill in the starting value for A, and then we're given a new value which lets us fill in time and the population at that time. So we know that 10 years later in 1869, right? So t equals 10. the population was 10 million. So let's write that down. 10 million. 1000. So 10 million would equal 100 e to the r times 10, right? So what we've done here, y'all, is we've plugged in the data we were given. And now we can calculate r using what we learned about solving equations with logarithms. Okay, so let's get started. I'm going to divide both sides by 100 to get rid of that 100 in front of the e. That gives me 100,000 equals e to the power of r times 10. Now, this is where we have a classic exponential equation where our variable is in the power. So we need to get rid of this exponential. We need to get rid of the e. To do that, we're going to use our handy natural logarithm, right? The natural log, if you guys remember, is an inverse of an exponential with base e. So these guys will cancel each other out. So what we get, let's go over here. We get that the natural log of 100,000 is equal to the rate times 10. Now, uh, now that we have ln of 100,000 equals r times 10, we just got to divide by 10 from both sides to get the growth rate, right? So what's that equal? Let me pull out a calculator. So the natural log of 100,000 divided by 10 would be equal to 1.15, about, rounding. Cool. And so then that's our growth rate. So we can then use that to find our model, right? So our model would be P of t is equal to 100 e to the power of 1.15 t. Let's box that. Cool. So we've calculated a growth model. Now what we can do is we could then use this to predict the population at various points in time. Um, like we could figure out, oh, what was the rabbit population 20 years later, 50 years later, so on by plugging it in, right? Something that's crazy here though. Look at that growth rate, 1.15. If we write this decimal as a percentage increase, we can see that the rabbit population is increasing by 115% per year. That's crazy. 115%. That means that the population is literally doubling, more than doubling every year. Now that's fucking like rabbits.